Hi friends, again welcome all of you to my channel on Structural Design 1. This session we are going to discuss another problem on the design of shear reinforcement. Now here this question is also I have taken from the previous question paper April 2019. April 2019 to design the shear reinforcement or to design the beam for shear. So that's the question. What are the data given in the question? So in module 2 you can see the question. The breadth of the beam is given B is equal to 250 mm. Effective depth of the beam is given as 500 mm. There are 4 bars of 22 mm dia on the tension side, or AST is equal to 4 into pi by 4 into 22 square. Then the material properties are given. FCK or M20 concrete, FCK 20 Newton per mm squared, and grade of steel is given. Fe 415, that means Fy equals 415 Newton per mm squared, and the span of the beam is given as 5 meter. Then it carries a load of, that is given including the self weight of the beam. The load is given as 30 kilonewton per meter. W equals 30 kilonewton per meter. These are the data given in the question to design the beam for shear. Okay, so what is AST here? AST is equal to 4 bars, 4 into pi by 4 into 22 square, or you can take it directly from the code. Okay, you will get it as 1516 mm square. That is the area of steel. It's given. Span of the beam is given 5 meter or 5 into 10 raised to 3 mm. Okay, now to start with, we have to find out the factored load. Here the load including the self weight is given as 30 kilonewton per meter. So what is the factored load then? Factored load is equal to that 30 into partial safety factor 1.5, that you know. We have to multiply with the partial safety factor to get the factored load is equal to 45 kilonewton per meter. Right? So first find out or calculate the factored load, and therefore what is the factored shear force then? Shear force, you know, in a simply support beam carrying UD load, what is the maximum shear? The maximum shear force at the support will be equal to WL by 2. The reaction, this is the reaction, and the maximum SF will be equal to the reaction at that point. That's equal to the total load is WL. So each reaction will be equal to WL by 2, WL by 2. That we studied in TS. Okay. So the maximum shear at the two supports will be equal to WL by 2. So the factored shear force is equal to WL by 2 equals 45 into 5 divided by 2. Isn't it? The maximum shear force is equal to 112.5 kilonewton is the shear force. Maximum or factored shear force is equal to 112.5 kilonewton. Then if we know the shear force, now we can find out the nominal shear stress tau V. What is tau V? V divided by BD. Shear force divided by area. That is the shear stress. We already done. Right? We know this formula and you will get it from the code also. Nominal shear stress is equal to tau V is equal to V by BD equals, what is V? Shear force 112.5 into 10 raised to 3. That much Newton divided by B is equal to 250 into effective depth 500. Right? So nominal shear stress tau V is equal to V divided by BD equal to 0.9 Newton per mm squared. So we got the nominal shear stress tau V is equal to 0.9 Newton per mm squared. Now what's the next step? We have to find out the design shear stress or tau C. We have to compare now tau V and tau C, isn't it? So to get tau C, what's the procedure? From the code, find out the percentage of reinforcement PT. What is PT? 100 AST divided by BD, isn't it? 100 AST divided by BD equals 100 into 1516. AST is equal to how much? 1516. Here it is 1516 divided by B is 250 into 500. The percentage reinforcement, the formula 100 AST by BD, you solve it, you will get it as 1.21 percentage. 1.21 percentage is the percentage of steel reinforcement. Now from the code, you know, for this value, for this percentage of reinforcement, exactly 1.21 percentage will not be there in the code. So nearest to that value for 1.5 percentage. 1.5 percentage of steel. What is the value of tau C from the code? You will get it. Tau C is equal to 0.66 Newton per mm square. Check that value from the code. Tau C equals 0.66 Newton per mm square. Okay. Now compare the nominal shear stress and the design shear stress, or the maximum shear stress. Here tau V 0.9 and tau C 0.66. Tau V is greater than tau C. So what's the conclusion? If tau V is greater than tau C, we have to design the shear reinforcement that is necessary, right? That is necessary to design the shear reinforcement. So for that, we have to find out to design the shear. Otherwise, what we'll do in the last problem? If tau V is less than tau C, we have to provide the nominal shear reinforcement. Understood? Nominal or minimum reinforcement. But here, since it is greater than TC, we have to design the shear reinforcement. For that, first find out BUS, right? All these are there in the code I told you in the last class. Refer that page and the tables. From that, you'll get the relation also. BUS is equal to BU minus tau C into BD, right? Tau C BD. That is VU is equal to how much? What is the shear? That is 112.5 is the SF. Is the SF? 112.5 into 10 raised to 3 minus tau C is equal to 0.66 into D 500. Effective depth 500. So from this, you will get VUS is equal to 30 kilonewton or 30,000 Newton, right? 30 kilonewton. Now, therefore, we got VUS value. Now, therefore, we have to assume the shear reinforcement. So, our question is to design the shear reinforcement. So, we are assuming the shear reinforcement as two-legged shear reinforcement. We studied already two-legged shear reinforcement like this. 8 mm dia, suppose we are assuming. You can assume it as 6 mm or 8 mm. Now for the time being, we are assuming 8 mm dia two-legged stirrups. Then what is ASB? What is the area of shear reinforcement then? 2 into ASB is equal to 2 into pi by 4 into 8 squared. 8 mm is the diameter of the shear reinforcement is equal to 100.5 mm squared. That is the area of shear reinforcement for 8 mm dia, two-legged stirrups, right? Now we can find out the spacing as in the previous case, the formula SV spacing. Spacing of shear reinforcement is equal to what is the formula? 0.87 Fi into ASV. 0.87 Fi into ASV into D divided by VUS. VUS we already got the value. Substituting this value here, 0.87 Fi is given as 415. ASV we calculated 100.5. D is equal to 500 divided by what is it? VUS, got it, right? So that's the spacing, SV. By substituting these values, we'll get the value of the spacing of the bars, spacing of the shear reinforcement. Okay, so that is when you calculate, it will come 604 mm, the spacing of reinforcement. So as per the maximum shear stress obtained, now we calculated the spacing to be given for 8 mm dia two-legged stirrups. But even though we got this value, we have to check the provisions as per the code. What is the provisions as per the code? Number 1, nominal shear reinforcement. What is the provision for in the code? Nominal shear reinforcement. SV is equal to, what is the formula? 0.87 Fy, we have done already now, into ASV divided by 0.4B. For nominal shear force, SV is equal to 0.5 into ASV divided by 0.4B, right? That we have already calculated in the last class from the code. This is the spacing for the what is it, nominal shear reinforcement. So that will be, when you substitute all the values, you will get it as approximately 362 mm as the spacing. Then number 2, again, what is it? We have to check 0.75D as per the code. 0.75 into 500. 0.75 into 500 is equal to how much? It is 875 m, isn't it? 0.75 into 500 is equal to, I think it is 375, right? You calculate this value, approximately 375 mm, and the last one, number 3, 300 mm. It should not be more than, as per the code, the spacing of the bar should not be more than 300 mm. So out of these, when we check all the provisions from the code for the spacing of reinforcement, the minimum is equal to 300 mm. Therefore, provide 8 mm dia two-legged stirrups at 300 mm center to center. So that is the design. So we have to provide shear reinforcement of 8 mm dia two-legged stirrups at 300 mm center to center, right? So that is the question here. So in this problem, when you check tau v and tau c, in the last problem tau v was less than tau c, here tau v is greater than tau c, therefore we have to design the shear reinforcement as per the formula given. Then again we have to check the 3 conditions, the 3 provisions as per the code: nominal shear reinforcement spacing, 0.75D and 300 mm. Out of these, take the minimum value as the spacing of shear reinforcement. So we got it. Now the shear reinforcements to be provided: 8 mm dia two-legged stirrups at 300 mm center to center. Okay, is it clear? So that is the solution for this question. Okay, now I'm winding up the class now. We'll see again in the next video. Okay, thank you one and all.